We have 11.
Hey, great. Well, welcome everyone. Thank you for coming to tonight's meetup. This is our first meetup back uh, since coronavirus has had us sheltering in place. We took a hiatus for the past few months, but are happy to be back and are looking forward to just having our regular monthly schedule, which is the second Monday of every month. So yeah, welcome back. Not too much admin from myself this time, other than we're back now and we're gonna continue meeting regularly. We're new to this format, the virtual meetup. We've been meeting in person for a little over a year. So if you have any suggestions for improvement or any ideas or whatnot, my name is Jason. Our other organizer is Tyler. Feel free to reach out to either one of us with comments, suggestions, or anything else. We're sponsored by Capital Factory. Normally we'd be meeting in their building, but alas, here we are. We're also sort of self-sponsored now. Myself and Tyler and another person have embarked on kind of an educational side project that's in part inspired by our participation in this meetup. We're both very kind of passionate about learning and teaching. So we're building a product that is the quote integrated learning environment. The idea is to kind of modernize learning with technical books in a way that's very hands-on and sort of realistic. So we have a website, trypragma.com. The product's not out yet, but we're just looking for feedback on what people want to learn in various topics. So it'd be super helpful to us to let us know what sorts of things you're interested in learning. That'll help kind of guide our initial efforts. For tonight's talk, as you all know, before I do that, Tyler, anything that I missed or you wanted to say?
No, I think you covered it.
Okay. Well, that's Tyler. So now everyone knows who Tyler is. Hey, tonight's talk is Clustering and Self-Organization Part 2 with Jacob. Jacob, thank you for coming back virtually for this. We really appreciate it and enjoyed your last talk and are certainly looking forward to this one. Feel free to go ahead and take over the screen.
Okay. I cannot share my screen unless you remove yours. So you have to stop sharing screen, then I'll take it. Okay. Now I can take the screen. And hopefully you're seeing my screen now.
Yes.
Okay. So the links here, as you can see, this is part 2 of the presentation. In part 1, you should be able to find it in January meetup. There's a link to a YouTube video. You can go back and look at it, but I'm going to give you a small recap. I talked mostly about clustering, less about self-organization. I'm going to talk about self-organization now, and if you have any questions, please jump in the middle, just unmute yourself, ask me, stop me. I rather have it more as a conversation than as a talk. I'm going to show stuff. I'm going to try to avoid equations, just show you the smart parts, but I'm going to give you references. Most of what I'm going to show is here. The links are here, and you should be able to find and download some of those things and run them. There's one more, I do have one more GitHub repository that is not here. I'll send it later. That is the neural network. Actually, it's here. Yeah, okay. It's the neural network, but actually it's a self-organization, not the neural networks you're familiar with. So you will be able to find some of it here and actually run it, even with some of the examples I'm going to show. It requires Visual C to actually go and compile it, and it will work on Windows environment. So let's start with what we talked about. I'll give you a small recap. Clustering algorithms. I'm going to show you what I showed before. This is scikit-learn, and those are clustering algorithms working in scikit-learn, the idea is that clustering algorithms, if you have data that is somewhat different and you want to figure out which of the clusters here, each cluster is a different, represented by a different color, there are multiple algorithms that can do that. Some of the algorithms are, I covered them, and you have some differences between them, and some of them behave differently on different data sets, as you can see. I covered this in the first part, and there is a connection to self-organization, which is what I'm going to talk about in this part of the talk, which is, and I'm going to start with k-means, but I'll start with giving you a little more information, and I'm going to remind you what clustering does. So this is what it can do to points in 2 dimensions, like cluster those different sets of data differently, and figure out what regions are there and how many clusters are. Some algorithms will figure out how many clusters, some not. The most known one is k-means. We're going to go into depth into k-means now and explain how it's related also to self-organization. Or not so much in depth, but a little bit more explanation. This is what clustering can do for you. It can find outliers in data. So if you have clouds of data, and I showed this and talked about it more, if you have like a graph of data, you can find, oh, this is the main part, and those points are outliers. And there are many, many algorithms that can do this, and you can use voting systems by running multiple clustering algorithms. So I talked about this. This is ICU data, and you have a link for that in the meetup page. And if you have more questions, just Google my last name. I should be first. You'll find my email and contact information. Ask me directly. I'm very easy to find. Another thing that we can use clustering algorithms for is natural language processing, where you can find all sorts of things that look the same text, and this is without the machine understanding anything. Clustering algorithms and self-organization are what's called unsupervised machine learning, because you don't explain to the machine what the data is, how is it classified. The machine kind of figures out, oh, it's a class, this is a class, this is a class. This is what clustering does. Splinters data into classes. So here, for example, using NLP, it will find things that look the same. And if I change a cluster to something that looks differently, and what I'm showing you is clinical units from clinicaltrials.gov. You can go to the clinical unit mapping website.com, and you will see the same thing, and you can play around and see how those clusters work. So here you can see all the units that look the same kind of clustered together, which is important for users who need to see them and figure out, oh, those are the same. This is why another use for clustering. I'll give you another example. Here's another cluster of units. And here are all the things that look like % of something. So the system was able to figure this out mostly by itself. It needs a little bit of help in some cases, but it does this mostly using clustering algorithms. So I covered those, and I gave another example in the last meetup. And we finished, it took a while, but we finished the point before we actually could talk about self-organization, which is kind of has an overlap with some clustering algorithms, and I'm going to explain those. But for now, let's start by explaining a bit more, and I have to move this, yeah. This is the main source of data. There's a guy named Brent Fritzke, a German guy. He did the most extensive work I'm familiar with on self-organization algorithms. He calls this competitive learning, but it is, but also it's important to understand what they are. And he actually went algorithm by algorithm and explained the differences, and also assembled a bunch of algorithms together and shows how they can develop into some other things, and some differences between them. So we're going to follow his path a little bit. In this website, you can see that actually the algorithm is working. You can actually press on something and see a different self-organization algorithm working. Some of those can be used for clustering, and you can play around with them. So demogng.de, highly recommended. You have to enable JavaScript to actually run this, but highly recommended. To get to the manuscript where actually he has all the knowledge written down so very well, there's a manual. If you go to the manual, you'll get to this page, but the actual manual, the good part in the manual is actually a PDF that he wrote, and you can download this in PDF format, and I'm going to show you how it looks like. This is his notes. This is like a draft, but this is one of the most extensive sources for information. Highly recommend if you're interested in some of those competitive learning algorithms. Those are self-organization algorithms. We call it competitive learning, but those are based on self-organization. You will see many of them, and you can see it in the topics. The topics are fairly well, and it's a very good read, and he explains it so well. He also gives examples, and you can follow it online and see what those things do. Very well. Very well written. I'm going to use it a little bit, but mostly I'm going to focus on things that I've worked on in the past, because when I was doing my PhD at the Technion many years ago, I was doing it at a CAD lab in Israel. CAD is computer-aided design. We were working on reverse engineering from laser scans. So we had laser scans. I'm going to show you one. Here we go. This is a laser scan of a body of a toy car. It's like a bunch of points, and the idea was to actually reconstruct an object that is built from those. So there are many techniques to do this from computational geometry. However, I was going into the machine learning techniques and trying to do some things with them. Some limited success, but interestingly enough, it went back into computational geometry and contributed a little bit to computational geometry while doing this. And I'm going to touch a little bit on this, but I'm not going to go into details. So there is a connection to computational geometry of all of those techniques, and I'm going to explain a little bit of this. So let's see, what should we start with? We can start with the basics, and I'll just follow the topics according to Fritzke. So the goals of competitive learning or self-organization are error minimization, entropy maximization, and feature mapping. Feature mapping is basically kind of related to clustering. You have data and you're actually trying to figure out, reduce the dimensionality of it. And this is one way of doing it. And you'll do this using those techniques I'm going to show later. Let's explain what error minimization is. But before this, I want to explain what a Voronoi diagram is. How many people have you ever heard of Voronoi diagram? And please answer.
I am not embarrassed to say that I have not.
Okay. So let's start with something simple. Here, you have a bunch of points. Those bunch of points, you want to find the sectors, the areas around them which are closest to that point. This structure is called the Voronoi diagram. The way you do this is you have very sophisticated algorithms, but basically you take the bisectors. So let's say this is the bisector between those 2 points. This is the bisector between those 2 points. And those connect here. This is the bisector between those 2 points, and more or less, and so on and so forth. You notice I'm starting to create some sort of structure that looks like, that allows me to find all those areas around this point and that point. So this point, the area that I'm now pointing it, or the point that I'm pointing it, is closer here because it's in that area of the Voronoi diagram.
May I ask a clarifying question?
Go ahead.
So the area around one of those points, like that bottom right X, are you trying to find the area that corresponds to that point or that corresponds to that cluster?
Closest to the points. Forget about clusters for now. We'll talk about the clusters later.
I see.
Like
Okay.
I have a bunch of points. I don't know about clustering or anything. What I want to do, and it's kind of related because the cluster also, it's like you want the center of the cluster to be represent all the points around it. So the Voronoi diagram of the cluster later on, we'll talk then. This is basically the closest points to a specific centroid. So this is how it's determined. And the centroids are the centers of the Voronoi diagram. It's a little bit funny. I'll show it in a second. But
Okay, I understand. Thank you.
But currently, I'm just want to tell you points. Now, here I'm showing it on points. I didn't tell you whether the point is a centroid or just a point sample point. But it doesn't matter. I'm saying if you have a bunch of points in space and you're trying to figure out what are the closest points to that specific point, this is how you do this by Voronoi diagram. So let me show you how it looks like. This is Wikipedia. You can see here you have a centroid, and you see this is the bisector between those 2 points, and so on and so forth. You build up this Voronoi diagram. Now notice your distance doesn't have to be Euclidean, which usually creates something like this. If you use Manhattan distance or some other norm, it will be something funnier. Because it depends on the point and how you compute the distance. But you can compute those Voronoi diagrams. Usually you use Euclidean distance, and there's some algorithms fairly efficient. You can also do this in multiple dimensions, only then the area becomes like in 3D, it becomes like lots of 3D structures around the point.
Yeah, solid.
You don't use a bisector, you use the hyperplanes to cut off it's a bisection hyperplane basically. So far I'm okay, you're with me?
Yeah, it makes sense. Thank you.
Okay, good. Thank you for the question, and do ask those questions. Like I want people to get it. So please. So because I'm skimming across a lot of information, and I'm afraid of losing some of you. I'm going to show you some nice pictures later, and I'm going to avoid equations as much as I can. So this is how this is the base of some of the ideas. Now think about it. If you are trying to take this plane and you have like really points and you're trying to find clusters of those points, those centroids that are now showing here will be the centers of those clusters, which is what you will actually find in k-means. Did someone completely not understand me now? I'm just connecting to the question before. Those centroids are trying to learn data that is more complicated. So let's say it tries to get sample, let's say you have a grid of points here, like every pixel here, and you're trying to figure out how to cluster those. And you do this with 20 points, like this is what you might get.
So this is if k was 20, right? And k-means?
This is k20 and k-means trying to represent this data. It's actually bad, but like this may be at the beginning of the process. So far, we're okay? Yes? No?
Yes.
Yeah.
Good. Good. Okay, let's continue. So now, let's go and explain the very basic k-means algorithm, but before the one that they actually, Fritzke actually has a distinction between the level of k-means that people are familiar with. What's known as batch k-means or LBG algorithm or Lloyd algorithm does the following, and I'll explain it on this diagram here. Hopefully you'll be able to understand what happens. So you have all those black points that you're trying to sample, and you're trying to cluster them using those two centroids. I say centroids now. I'll use the term neural units later, or just quantizing vectors. Those are all terms that can be changed interchangeably. So here I'm trying to cluster those using k equals 2. I'm trying to find two clusters here. Even though it doesn't make sense, I'm trying to figure out, separate this data into two clusters. So I start randomly by putting those over here. The way it's going to be done in k-means, not k-means, I'll say LBJ. By the way, LBJ and k-means are sometimes interchanged. People, not LBJ, LBG and k-means are sometimes interchanged. So the way I'm going to do this, I'm going to create a bisector. This is the Voronoi diagram between those two centroids. So far, we're okay? The Voronoi diagram between two centroids is very simple. It's only the bisection.
Yeah,
Now
that makes sense.
Now I separated the world into two clusters. One of them is all the points underneath that line, and one of them is all the points above that line. So far, we're okay?
Yeah, yes.
Good.
Making sense.
Good. Now, what's going to happen in the LBG algorithm, this point is going to move to the center, to the average of those points over here. It's approximately average, correct? Center of mass. Correct?
Correct.
Good. This point is going to move to the center of all of those above the bisector, all of those areas about somewhere like this. And then we continue the process again. We delete that line, and I hope there's a deletion thing here that I can delete it. Here, I'll delete it like that. Good. And then I'm going to continue by doing this again. This time the bisector is somewhere a little bit different. Let's say it like this. Oops, sorry, wrong thing. Sorry, wrong line. Here's the line thingy.
So you're just assigning the point to the closest centroid, right?
No. I'm computing the Voronoi diagram.
Oh, okay.
I'm computing the Voronoi diagram, and it's called batch because you look at all the points in the Voronoi diagram and then you apply it. Then you do the correction. So then this point will move somewhere over here. After each time I compute the Voronoi diagram between those two, and then this point will move somewhere over here.
You're right, but how did you decide the position of the separating plane?
It's a bisection, bisector.
Oh, okay.
From geometry, like elementary geometry.
Between the
You
two
connect the line and then
Yeah. No, I get it. Okay.
The Voronoi diagram with 2 points is a bisector.
Yeah. So it's just perpendicular to the line between the points, right?
In the middle.
Yeah, I get it. Okay, it's simple.
And this separates all the area closer to 1 point, meaning cluster A, and then the other point, cluster B. So far, so good? So this is what we just did. It's called the LBG algorithm. This is the base for k-means. Now, let's go back. Okay. You can do this. This is the Lloyd algorithm, the one. Many times it's confused with k-means because they are very similar. What they did later, and this is where we start going towards a little bit towards how the self-organizing algorithms work, many of them, we're going to make a little step and we're going to call it online, meaning we don't want to learn all of the points as a batch. Each time we're going to use each one of those points and we're going to teach each iteration each one of those points is going to teach the centroid a little bit. So now the algorithm will go something like this. I select that point. This point, I compute what is the closest centroid. This one. This one is closer than this one. Oh, if this one, what we're going to do is we're going to move that point closer towards that point in the line in the same direction. How much? This is according to a specific learning rate. And you say how much it gets close. So let's say half. Each time it will happen, we'll jump half the distance towards the points that attracts it. So we've done this for this point. We then select this point, and this point says, oh, this one's closer, so we're going to move this one half the distance towards that point. Then we're going to do it again. Let's say this point is selected. Oh, this point is closer to this centroid. We're going to close half the distance here. And then let's say this point. Oh, this point, from those 2 points, this one is closer. So we're going to move it half the way towards here. It's not very accurate, but yeah, I'll do it more accurately. Oops. It will move something like this. And this will continue again and again and again and again. However, this algorithm will have problems because if, for example, we select this point, it will go towards this, and then this one selected, it will go back, and then go back here, and then it will go back here, and so on and so forth. It can be like kind of twitchy. So usually what we do, you start decreasing the learning rate. You say, okay, at the beginning, I will advance half the distance towards the point that I want, but later I'll go and say, okay, I'm going to advance a little bit less, let's say a third. And then I'm going to advance even less, a quarter, and so on and so forth. This way, eventually you'll get to the point that even if you find new points, you barely move the points. Even if you find like a new centroid, you do, sorry, not move the points, you barely move the centroids, apologies. The neural units, the ones that represent your cluster center. This is what happened, and this is what became K-means. K-means is a specific variation of this online algorithm where the learning rate goes down. I think it's 1 divided by t. We can actually check it in Fritz. Let's double check. I don't want to say something wrong because, oops, sorry, not this. You see, he explains all of those things. Oh, I forgot one thing. Sorry. I forgot to tell you about error minimization. Error minimization is you're trying to minimize the error between all the points in the Voronoi diagram towards the center of the Voronoi, towards the centroid or towards the neural unit. You're trying to minimize them. So this is what those self-organization things work for. And another thing is entropy maximization is where you have areas of different density and you're trying to mimic the same density with less points. Those are the uses for self-organization. And of course, feature mapping and clustering. So I forgot. Yeah, sorry.
Sorry, Jacob. Could you expand a little on what you mean by error minimization? Like what the error is or are?
So the error is if you have a bunch of points here. Sorry, I wanted to talk about the LBJ and K-means. Let me finish K-means and I'll go back to this. Okay.
Sure. Thank you.
Apologies. So here he explains it well, but I just wanted to check out that K-means. I'm not telling you that here. K-means. This is the learning rate, 1 minus time. So like the first step, it will be a full distance, second step is half, third step is third, and so on and so forth. Within time, it should converge, but there are some issues with convergence here. Go read the paper if you're interested in what things converge and what not. But generally, people use K-means and it works pretty well, even if there's no proof of convergence, and we can argue about convergence. Let's say it like this. He actually mentions it. So let's not go back. So let's go back to the error, to the quantization thing. So I'm going to show it to you. So error minimization, you're trying to minimize the error. So here is the formal definition. I'll just show it to you. It's an equation. I tried not to go to the equations, but I'll show it to you. This is Fritzke. He does a very good job in explaining those things. Blah, blah, blah. Here. He's trying to minimize the error within. You see, VC is the Voronoi diagram of the centroid, specific centroid. So he's trying to figure out the distance between all the points in the centroid and in the Voronoi diagram. So this represents all the points. So let me show it to you visually. So again, the example before, here we go. This is the Voronoi diagram of this example, those two things. I'm trying to make such that all the points, the distance to this center, the sum of this is as minimal as possible. So I want basically, in the situation that it is now, it's fairly large, but if I select that point and I move it over here, it will be smaller. Why? Because I'm closer to those points. And I'm only concerned about the points in this area. This point will be, the error will be better if it's in the center of mass of those points. This is what error minimization means.
Okay, I understand. Thank you. Yeah, thank you very much.
And you can look at the formal definition. And frankly, I'm trying to avoid equations. Some of them I don't remember well. I've done this a long time ago, so it takes a lot of effort from me as well. But Fritzke has a good explanation, very simple one and very good. So follow him. So this is what I explained. This is what it is. This is what it's used for. And I explained LBG and K-means. Those two algorithms are the base, and those are the connection for this next set of organizing algorithms. Because you remember, we started by the idea of looking at the Voronoi diagram and then taking all the points and trying to average them and put this the point in the center. This is what we started with, but later on, where the algorithm said, oh, we're using it each time we're moving this point only according to closeness to the last point that it's, with moving the centroid according to the last point that we sampled. We call it a sample point. The sample point represents the data we have. So for example, here we have many, many sample points, like I think 10,000 or more, 100,000 can be, I don't remember the size of this. But we have many points, and we are trying to represent this using less information, using self-organization somehow. So, hopefully I explained it well enough. Up until now, people are barely with me at least. Did I confuse you too much? Do you have any questions so far?
I'm with you. What was the, what did you say right now about the car, about the toy car?
So look at the toy car. It's composed of many, many points. These are sample points. They actually represent samples of the surface. I'm trying to represent the surface of the car. It's,
yes,
here,
yes.
I'll show you.
Yes. Yeah.
It's a surface. I'm trying to represent it somehow.
Yeah. Because infinite points don't fit in memory.
What?
I said because infinite points don't fit in memory.
Actually, not about that. The points themselves don't have information about anything about topology.
Oh, I see.
You don't know what the connection between points is. It's like water. It's like soup. Think about it. It's a soup of points. You want to find the connection between them that represents the body.
I see.
Make sense?
Yeah.
Good. Thank you. Thank you for being with me. And do ask questions, please. So the first of the algorithms, I'm going to go back. Forget about what I showed you before. I'm going to show you the first of the self-organizing algorithms that that was created, that as far as I know, actually after K-means probably, but because K-means kind of falls in this competitive learning. we're going to go ahead and let's take the car. And this is the software you can download in rectangular topology, and let's make it 10 by 10. The first one was something called self-organizing feature maps. It's usually if people drop the feature, they just say self-organizing maps. So here's the car again. I'm going to adjust a little bit so we can see it a little bit better. And you can see all this mesh around it, like all those lines, greens and reds, and those black lines. Think about it as a fisherman's net. Like, have you ever took a fisherman's net like this grid and kind of put it all together, like scramble it together, like
Christmas lights?
What?
Like Christmas lights?
Yeah, Christmas lights that are usually on the line, but yeah, okay, yeah, it's a good idea. Think about it as Christmas lights on the line, but you have a grid here. Fisherman's net is actually a grid. So let's make it a little bit more visual friendly, and we don't need this. Good. So you recognize the car underneath all this mess? If you don't, I'll enlarge it a little bit. Okay. Now, what I'm going to do now, I'm going to ask the system, and I'm going to show you what self-organizing feature map does. Again, Kohonen is the name. He wrote books. He wrote a very good book about it called SOM, Self-Organizing Feature Maps, or SOFM or SOM. Sometimes it's like SOM. But if you look at Kohonen, you'll find it. So I'm going to run this algorithm, and you're going to see what's going to happen. Very quickly, you see the net forms. And this net is trying to learn the picture of the car. And you can see, forget about the size. Every once in a while, you see things expand outwards, like the border expands. This is my enhancement. But like otherwise, what you see now, the net started unordered, it became ordered. How did it happen? Well, we're going to leave it to run. We're going to go back to it. You'll see it later in a better shape, hopefully. Even now, if I rotate it, you can actually see it. It starts to take the shape of the data points. But notice now you know in the grid, you know which centroid is near which other centroid. And you have information about connectivity now. And this is something that you can actually draw a surface with.
Is the number of points in the grid a hyperparameter?
Yes. Well, we're going to talk about the number of points in a second. You're ahead of yourself. You're ahead. We'll get to the number of points. I'm trying to explain some different concept. We'll get there. Good question, though. Okay. Oh, actually, you see, it's already like gotten the shape pretty well. So it learned unsupervised, it learned the data. Now notice, the surface is two-dimensional. It lives in three-dimensional, but the surface is a two-dimensional creature. Think about it, it's like a sheet of paper that you go and you bend to form whatever you want shape in 3D. And this is what Kohonen's self-organizing feature map does. It takes this three-dimensional information and compresses it in 2 dimensions. Now you can figure out in 2 dimensions, you can actually generate a surface on top of it. And this is what I was doing in my PhD a lot of the time. So let me show you the self-organizing feature maps algorithm. So whenever you say N here is a neural unit, it's the centroids, and those are basically the centers of the grid points. The idea is you initialize them somewhere randomly, you pick a sample point, you find the closest parametric point on the grid, the neural unit on the grid that is closest to the point. You update of the position of this neural unit towards the grid. Also, you update the neighborhood. And we'll talk about the neighborhood in a second. I'm going to show it to you towards that sample point, just like we did with k-means. You remember the k-means algorithm where actually we moved a little bit towards? It's the same here. And then you increment, and then you do this again and again and again and again. And you always reduce the learning rate as well. This is the self-organizing feature map. I added several more extensions to it. If you want, you can read my PhD. But it's a very good one. Let me show you how it works here. So here, let's delete those. We don't need those units anymore, not for now. And we now have a grid. The algorithm says, find the closest neural unit to that point. You have a sample point. Each time you sample one sample point, find the closest neural unit. This is this one. What you do is you move it a little bit towards that point. Now, neighborhood is very important because in self-organizing feature map, you actually know who the neighbors are according to who is on the grid. So you see, to this centroid or this neural unit, those 4 are the closest. They are distance 1 on the grid. This one is distance 2 because you have to go 1, 2. Those also move towards the grid, towards that point. So for example, this one will move a little bit less than the main unit. This one will move a little bit less than the center unit, and this one will move also a little bit less. All of those will move. However, we haven't finished. You look several more, and those look a little bit less, those like, and you continue until you have a function where you stop doing this. But generally in SOM, you actually do this for all the neighborhood. You actually update the entire neighborhood towards that sample point. So think about now the sample points is like magnets towards the centroids that each time you represent one, it attracts them. And you repeat the process so many times that eventually it converges. And let me show you how it converged. It converged to this. Now you can actually eliminate the points, and I'll do this. Yeah. You can actually figure out what was the shape from this. So far, any questions? Understood? So this was Kohonen. Kohonen, I think we can eliminate that, stop this one from running. So Kohonen was one of the first ones who did that. And here the topology is fixed and the size of the grid is fixed. One of the questions you were asking me is about whether the size of the grid is a hyperparameter. Yes, it is. But now let's add a little bit more complication. Let's take this car again, only now we're gonna do something called growing grid. Sorry. Actually, let's take a mask. Let's see if it's big enough to actually show. And we're still doing something rectangular topology, but now in our hyperparameters, we said the grid can grow. I'm going to explain it in a second, but this is no longer a self-organizing map. This is something called growing grid. It's almost the same algorithm as a self-organizing map, only at the beginning, let's take a real mask so you can see what I'm doing. Yeah. Okay. What you see here is, this is not laser scanned, if I recall correctly. This is like reproduced geometrically using software, or maybe it's a mask. I don't remember at this point. It's a long time ago. But yeah, it looks too good. Probably, yeah, this is not a laser scan probably. But you can see a human mask here, correct? Now, how many features do you actually want to do this? So you remember the fisherman's net at the beginning? It was 10 by 10 before. Now it's 3 by 3 size, and it starts unorganized. What I'm going to do now is I'm going to ask it to learn. I'm not sure if this is enough, but let's try. Maybe it will be good enough. What's happening now, this is glowing grid. It actually glows the grid, and instead of a 3 by 3, you'll see it will add rows and columns while learning. The way it does this, it does the same algorithm as before, only every once in a while, it will add another row or column in neural units that are winners all the time. Some neural units are more demanded than others. Like, and I'm going to show it to you from the side, and actually we don't need the, yeah. You can see it captures the mask. If I let it long enough, it will eventually be much, much more organized, but it will stop at some point. But you can already see I'm capturing the 3D object, and this algorithm, the glowing grid, grew on its own. And it's also, nice thing about it is it figures out what is the correct aspect ratio. Meaning if I have something very thin and long, it will create enough grid lines to actually, that the representative grid will be as long as thin. Because if you remember, one of the things those algorithms will do is it will capture the density of your data. So if you have more dense data in one place or another, you will see more points. So did I answer the question of the glowing grid about the hyperparameters?
Yeah, thank you.
Yeah, okay, good, good, good. So, and I'm going to show you this algorithm. Where is the, here we go. So this is the SOM algorithm, and here we go. We should have a glowing grid algorithm. It's very similar to it. You can find it in my PhD, but this is extension, and here. So every unit returns the win counter that accumulates number of times it won. And whenever, every once in a while in time, like in spaced period, like let's say every 1,000 iteration or something like this, you go and you check out the neuron with the largest number of wins and the direct neighbor with the second largest of wins that's connected to this neuron. And then you add a row or column in the middle. So this was glowing grid. So those extensions are what we call fixed topology, because I told the neural units how they are organized, what's the connection between them, between each other. I told them you're organized as a grid, as a fisherman's net. However, you can do it with different structures, potentially. Only it becomes much, much harder. Those algorithms work well with simple topologies. However, self-organizing algorithms can actually learn topologies. But before we learn topologies, let me show you something different. And once you saw a self-organizing map and neural grid, let's go into an algorithm called neural gas. I think it was Martinez and Schulten, but Frinsky explains it very well. Let's go back here. I'll try to explain neural gas to you. Good. So you remember the same algorithm as we said before? By the way, it's called hard competitive learning because the winner takes it all. It's the hard competitive learning. So within neural gas, you remember just like k-means, you take the neural units and you start the positions of the points, and you take a sample point, and then you take the neural unit and you find the nearest one. But let's forget about the fact that it's nearest. Just calculate the distance between it and all the points. And all the points will get nearer, only some will get closer. So this sample points will attract all of the points here. So this point will move towards it. Sorry, not point. This centroid will move towards it, the neural unit or whatever you call. But then this one, and then we select that point, and then this neural unit will work towards it, but then that one as well. And this continues again and again and again and again. Each one of those, if it's closer, it's attracted more than if it's not. This is basically neural gas. You can go over the equation. There's like several factors of deciding how close each point attracts all the points. But this is basically neural gas. Let me show you how neural gas works. Neural gas does not have, let's finish this. Let's take a helmet. This is an actual toy helmet that I played around with all the time, and we'll choose the algorithm neural gas. And we'll start with just 100 points. And we want neural gas. I'm not going to show you the Hebbian. We're going to talk about Hebbian learning in a second. Hopefully it will be good enough. Okay, so you see, it's like just a bunch of points. And we want those bunch of points to organize themselves on a helmet. Now notice the helmet has holes. You see the hole? Does anyone does not see the hole? Yeah, I'll make it bigger. It's a toy helmet and there's a hole inside. Because just like a real helmet, the visor is a hole, but think about it, in topology, in mathematical topology, this is called the genus 1 object because it has one hole. Genus is basically the number of holes you have in the object. So what neural gas will do, and I'm gonna just run it and show you what will happen. Show points, show neural, put it like that. Not row faces, points and neurons. That's it. So you see the black thing on neurons? And what's going to happen is I'm going to run it. What's happening is that the neurons are trying to arrange themselves as good as possible on the face of the mask. And it finished after a while. So now if I eliminate the points, I don't know if you can recognize the shape, but they are arranged on the faces of the mask. No, sorry, not mask, the toy helmet, sorry. Okay, did I lose you all or some of you are still listening?
Oh, we're still listening.
Okay, interact, please. If you see something funny or please give me hints. So let's do it again, but now let's introduce something called Hebbian learning. Hebbian learning is actually a machine learning concept. It was thought of by Hebb. I think 56 or 57 is the paper. You can look it up later. But Hebb decided that there is an element when two neurons on the brain are firing together, the synaptic link between those becomes stronger. So this is the concept that was there. Like neurons units that work together are connected strongly. Now, Schulten and Martinez took this a little bit further and they said, you know what, let's find the computational geometry explanation of this. And I'll try to explain it as simple as possible as I can. But let's say it like this. If you have, well, let's draw another neural unit because we'll need it. Another one, another one. Good. What they said is the following. What we're going to do is we're going to find the closest unit and we arrange them according to the distance. This is basically what neural gas does. It arranges all of those neural units according to the distance from the sample point, and then according to the distance, the closer one are attracted more than the farther ones. So Martinez and Schulter said, you know what, when you do this, take the two nearest one and add a link between them. Actually, put an edge. So if this is the sample point, this is the nearest neural unit, who's the second nearest? Probably this one is closer to this one. So what's going to happen is those two are now connected with an edge. Then you select another one. You see this point? This one is closer to this one, but the second closest is this one. So we'll draw an edge. And let's say this one, actually this one. This one is the closest one. The second closest will be this. We draw an edge. What did I just draw? A triangle. But what really did I do? What they did is they actually have a proof in their paper. This is part of the Delaunay triangulation. What's a Delaunay triangulation? This is you remember the Voronoi diagrams I showed before? If you take those bisectors and you actually draw the line between those, you get this Delaunay triangulation, and it's proven to be a very good triangulation. It creates very good meshes. I won't go into details, but this is actually computational geometry coming back from machine learning. So this concept that I'm showing you now can be extended to faces. This is what I did in my PhD. I actually extended it to faces. So let me show you now how neural gas with Hebbian learning looks like. So we'll take the same helmet thingy. And Jason, if I'm taking too much time or not interesting, let me know. I can stop wherever you want.
Oh, very, very interesting. And I will let you know about time if we approach our limit.
Notice neural gas has no topology initially. However, it detects topology, and you will see it happening in real time. If everything works well, sometimes things don't work. Yeah. No, not going neural gas. Gas and competitive learning. Let's do it quick. If not, we'll do it slowly. Actually, let's do it. This is still a little bit too big this time. It'll take a little bit longer now. So we have 100 neural units, and we're trying to represent this object with 100 neural units. So the lines represent normals. This is another extension, but for now, just forget about those. This is what neural gas does. It tries to capture the shape, but notice there are some, I'm gonna remove the faces for a second. You see those edges being formed every once in a while? This is the Hebbian learning. The system figures out what are the edges, and you know what, we're not seeing all the edges. Normal size, normal size. Actually, yeah, you can see it well enough. You can see the edges, the red ones being formed. Can you see them on your screens, or is it the resolution is good enough?
Yeah,
No,
yeah, we can see them.
Ones. Good. I'm going to do the following. I'm going to remove the neurons. Now you can see the picture. You can see a mesh being formed.
Mm-hmm. Yeah.
And we're going to remove the point. Can you recognize the helmet object?
Looks like a helmet.
Yeah, it's like a 3D mesh, but let's show you one more thing. And this is an extension I added during my PhD. If you want to learn how I did that, there's a proof. But now you can see the helmet.
Wow.
And you can see the hole. So I compressed this 100,000 or whatever number of points that were there, maybe 40,000 points or something, into less than 100. I compressed the data.
What would this look like without Hebbian learning?
Blue.
What?
What would this look like without Hebbian learning?
I showed it to you before. Hebbian learning is what creates the connections. It detects the topology. It does this locally. The Hebbian learning, here, without Hebbian learning, it looks like that. This is without Hebbian learning. I see,
okay.
Because you have no connections. It just finds, think about it as a clustering algorithm, like where we actually find the centers of the clusters of the data there, which is kind of meaningless to do for geometrical data like I said, unless you have some special feeling of like taking the data and figuring out what's new, but there are better techniques to do it than this.
I see.
So far we're on the same page. More questions, please. If anyone has some, I'll show you back the question.
I was just going to ask, what's the difference between the red and the pink and the blue lines?
So the red are the Hebbian learning, and notice, you see how nice the triangles are? Like they're almost like, the triangles are like almost 60 degrees angle. This is because Delano triangulation tends to do this. It's very nice triangulation. It finds the position such that the triangulation will be very, very easy. It's very good eventually even for visualization. So, and notice how everything is approximately spread apart. And the blue ones represent a whole. The system is unable to complete. You see, a human understands that there's another edge here. But once learning, the system will not be able to determine that there's an edge here because the way it happens. The way it happens is the edges are formed and there's a learning mechanism for the edges in Hebbian learning. There's also a forgetting mechanism because once an edge is formed, it may be formed in earlier parts of the learning where, you know, the data was still scrambled and not very accurate. Well, the mesh was kind of like very in the middle or not very representative. Only in later parts of the learning, the triangles, the edges are really meaningful. So
when it finishes, everything's red.
So therefore, there's a forgetting mechanism. Every edge that has not been updated for a long time disappears after a certain number of turns, of iterations. So think about it, it's like forgetting. It's like you forgot something. It's probably not important. This is the mechanism. This is part of the learning mechanism that are being used here. So the edges here represent actually geometrical edge. The purple ones are ones that tell you this is from a geometrical point of view cannot pass. It's something impossible or something not good. There's an algorithm to remove them later, but and there's algorithms to, let's see if it works here. I think what we can do is, if I remember it correctly, now this changes this. Yeah, you see, there's an algorithm that removes things that are impossible, and then you have to triangulate the rest. There's an algorithm that does this. Okay, this is not machine learning, but if you're trying to reconstruct the object, sometimes there's things that you have to look at. There are also rules in how to create meshes, and I'm trying to make them. But the neural units, the self-organizing learning got me to a certain point that you can actually have this knowledge. And it learned it without me actually telling it too much. This is the point. And this is what self-organization did. It puts the centroids close to where I wanted. The Hebbian learning actually created those edges. And my extension, it actually was able to create the faces.
Okay, thanks.
So far, it's good. Good. Now, let me show you the next evolution. So you remember, like, self-organizing maps was a grid of a certain size, and then someone asked me about, oh, those are hyperparameters you have to tune, and said, yeah, but the algorithms that do this, like the glowing grid, actually takes self-organizing maps and makes it better. Same thing here. There's something called glowing neural gas. By the way, it's called neural gas because the neurons are like gas. It's like if I don't connect them, they look like gas, as I showed you before. This is how they look like. It's like a gas of particles. So there's something called glowing neural gas. Let's take another picture, something interesting. Let's take a torus. Actually, let's take a teapot. What do you want, a torus or a teapot?
Let's do a teapot.
Teapot, okay. It's not very interesting, but we'll do it. And we're gonna use glowing neural gas. The neural gas will, again, start with 3 neurons. But very similar to glowing grid, it will grow. And let's give it a little bit more time. Let's update it, not every, let's do it even more time. Let's just let it go. So here's the teapot. This is artificially sampled. This is like, there was a geometry library called URIT that I was using in the Technion. A guy called Gershon Elber wrote it, and I was playing around with it. And this is like an artificial sample of a teapot that he had there. But whoever was doing any graphics, they know that teapot is something that everyone likes to show in graphics. So you can see the points are very nicely ordered. So the 3 neurons are the 3 of this. They start similar to a triangle, and we're going to just run it, and hopefully my parameters are good enough so it will grow. What happens now is very similar to what I was showing you before. The edges are being formed. Only every once in a while, the system decides, oh, you know, we need another neural unit. How does it decide it? Because the error of some of the units becomes too large. And every once in a while, it also forgets things. And I'm going to remove some, you know what, I'm going to make the teapot very, 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 very small so you can actually barely see it. And I'm going to remove those normals so you can actually see what's happening. There's the normals. Yeah. Okay.
Jacob, I have probably a very ignorant question.
Right.
The red triangles, that's formed by the Hebbian algorithm?
So the triangles are actually, the faces, the green faces are formed by an extension. Read my PhD and you'll figure out how I did that. It's an extension of what the Martinez and Chulton did. What they did is they formed the red lines. Sometimes you will see the lines are being blue and purple. Purple means there's some geometrical problem there. Blue means that incomplete, meaning like this is like on the edge of the surface. But yes, the Hebbian learning learns those, the Hebbian learning is what learns those, what learns those edges. The edges themselves are formed by Hebbian learning. The faces by an extension that I made.
Okay, so I guess my question is what determines the length of the edges?
Nothing determines. It's the position of the neural units, the position of the neural units. Think about it. What moves is not the edges. What moves are the neural units. Those get attracted to those sample points every once in a while. Think about it as like gas that's being attracted. You understand? Like gas particles being attracted each time to a different magnet, where the sample points are magnets. So those kind of like, think about this, they move all the time.
Thank you.
So this is how they started. Now you can already see that like, this is already forming. you can actually see the shape of the teapot. You can see it on top. So the edges are just say those neural units are close to each other, meaning there was a sample point that triggered them both. One of the points were the closest one, the second one was the second closest. This is what the edges mean. This means at some point in time, later on, some of the edges are being forgotten. You can adjust the parameters of those being when things get forgotten and when not. So this is glowing neural gas for you. I hope I didn't confuse people too much. We can let it run or let it run on some other objects. But at this point, I think I gave you a pretty good explanation of what self-organization is and how is it related to clustering. Did I make myself clear, or do you have any questions? Please ask them. I do expect questions. Otherwise, I will think that my time was in vain.
So, Jacob, you know my work and that it's totally different from this.
Yeah.
What are some practical use cases of these type of approaches? So
I showed you, Chris Leonard does some linguistics, actually computational linguistics. Chris, do you want to say 2 words about what you're saying better than me?
About us? I was really asking what the practical use is this.
So
my company
before I show everyone practical uses, I want you to explain things that you're doing. Just to explain, just give me 2 sentences or 3 sentences what it is you're doing, and then I'll show.
I'm the technical co-founder of a startup working with cognitive linguistic algorithms, original cognitive linguistic algorithms.
Okay, so basically, Chris is looking at text and trying to figure out all sorts of things from the text computationally. He uses all sorts of machine learning algorithms, but also some other algorithms that were tailored specifically for the text. I explained it very simply. Talk to Chris afterwards. He'll give you much more information about what they're doing. How is it related? Here I'm showing you 3D points. Those points represent geometry that I scanned from a laser scan. I'm going to go back to what I showed you before. At the beginning, actually, I showed it in clustering. Here we go. I have problems locating it.
And when I say practical examples, I mean, what would a company do with this?
Well, it depends. What I showed you is research.
Yeah,
Those are algorithms that people can think about. But I showed you clustering algorithms. Clustering algorithms, the algorithms I just showed you, like self-organization, they can be used for clustering. Think about it. Here, I'll show you the image again, and then I'll go back to this. You see, this point, this neural unit here represents all the points around it, correct?
Right.
Here, there are points. I made them a little bit harder to see.
I can see them. I know what you're talking about.
Good. This neural unit here represents all of those points because this is how they clustered. If you ask what's the cluster, what's the Voronoi diagram, what's all the points in this Voronoi diagram, it will show you all the points here. So those points belong to a certain class. In 3D, for the things I'm showing here, it's not very relevant to the way I classify it. Because I'm not doing classification here. I'm not doing clustering. I'm doing something a little bit funnier. I'm trying to figure out something else. However, Habian learning, what it tells you, it says also, oh, all those points belong to this unit, and all those points belong to this neural unit. And those neural units have a connection between them, meaning they are related somehow, they're close to each other. Not only topologically, not only geometrically the location, but also topologically, there's a connection between them. And you can actually see how many connections they are apart. You can see this neural unit is 5 connections away from this one. Now, think about it more. You see this neural unit here, and something that might be close. Let's find some good example. Here on the snout, there's a neural unit on the snout. I'm going to show those a little bit better. I messed it up. Okay, sorry. Press the wrong button. That's something else. Let's do.
I get what you're saying about the relationships between the.
Yeah, but I'm trying to tell you there's a topological relationship and there's a geometrical relationship. Those are different. And this is important to understand. Let me show you again. Let me show you on the torus. Or on a mask, which I'm trying to figure out which data example. The helmet is a good one. Okay. We'll do neural gas here, and let's do it 100 units as before. We'll just run it as before. This is important to understand because there's a topological distance and then there's the, no. Here, that's good enough. Let's eliminate all the faces. The points we do want neurons and we want the edges. Good. So I know how though easy it is to see, but let's take this neural unit and that neural unit. You see this one and that one, the two black things?
Yeah.
Chris, are you with me?
Yep.
They are geometrically close to each other. They are on both sides of the helmet, of the hole in the helmet.
Right.
However, they are not connected to each other topologically.
Right.
Good. This means they are not close to each other, even though they are close geometrically.
But they don't have a topological relationship.
Yeah, this means they are not close on the surface. So think about it in linguistics. If you have surfaces or some other structures that represent how units are relating or how words relate to each other, you can use things similar to this. I never seen anyone do it, but in let's say there are words that are close to each other lexically, but their meaning is very different.
Sure.
Correct? So using techniques like this, you can actually figure it out, because if you find sentences in one word and the other, so they may be close lexically, but they can mean something completely different, not lexically, or used in different sentences or things like that. So using Hebbian learning might help you figure out differences between things. Does it make sense?
Or more importantly, relationships between things.
Though relationships is like, as I told you, Hebb's law has something to do with two neurons firing in the brain at the same time. Here it's applied to geometry. You can apply in Hebbian learning to your algorithms something a little bit differently. Do I make sense?
Just imagine this and see what you think, and then I'll pass the mic. So imagine the Enron email data set, and you run the entire corpus and pick two related measurements that we take and do something like this on that data. Would it show relationships between people or events or periods of time in a way that we can't do just linearly?
So it depends what your exactly algorithm is, because here you have to translate it to geometry. Can you translate it to points in space, like vectors in space?
Perhaps.
If you have a vector in space, n-dimensional space, you can run those algorithms on it. Here I'm running two three-dimensional vectors in 3 dimensions because the points are in 3D space, the sample points. And I'm trying to figure out clusters or centroids that represent them. So this is the first thing. And then I connect those clusters together using Hebbian learning. And those are learned at the same time. The algorithms are fairly easy. I'll show you the algorithm. This is from my PhD, but you can copy it from Fritzke. So growing grids.
You and I can talk about this later because we know each other. I don't want to get in the way of anybody else who has questions.
Yeah. Anyway,
I get
this
it.
is the algorithm. Very simple. Anyway, please, we can talk later, but there are applications, a few things. A, it's not perfect, as you saw. Even in 3 dimensions, it's not perfect. But then machine learning is also not perfect many times. So the question is how good it is and whether it does something that you wanted. If you do, please, I'll be happy to implement something like this for you, or help you implement it or whatever.
It's an interesting thing to play with and see if there's something there.
If there's something there, I'll be happy. Let me know. If not, well, those things are not perfect. The second thing is you will have to compress the data so you'll be able to use it. So first thing you have to have your data is vectors. So that's the 2 things that I can tell you now. And of course you have to figure out the distance function, but because you don't have to do it with the Euclidean distance, you can do it with other distances.
Okay.
Hey,
Any
Jacob.
other questions? Yeah.
Yeah, I had another question. So what we're talking about doesn't have a direct application to my daily job, but I do have a friend who is working on some speaker diarization where he's trying to isolate different identities of people in an audio stream. And this seems, especially the LBG stuff, seems uniquely suited for that application. Do you know anything about that, or any information I could pass on to him that might help?
So look, this is unsupervised learning techniques. Usually unless he doesn't know anything and he wants to kind of like find clusters of data, sure. But then again, the question is, those algorithms are not always very accurate. As you can see, you have to play with a lot of hyperparameters to figure out what's good. I suggest start with clustering algorithms, not with what I just showed now. What I just showed now may be more applicable, self-organization may be more applicable to what Chris is doing. Maybe there are applications somewhere else that I don't know. Look, those are unexplored territories. People don't know that much. This is a good thing to experiment with. If you want data to start, not data, if you want to like edges of things to start working with, I suggest look at the Fritzke document, start with the GNG demo, the one I showed, and here, I'll show you
Those
the
are all-
websites again.
Those are linked in the meetup page, or no?
Yeah, all of those links should be there. So one of them should be the scikit-learn one. This gives you some information on clustering. Start with that because this might be your best bet. I'm not sure though. And then later look at the GNG demo, which is gngdemo.de, and for some reason it's, here it is, just loaded. So, and then you can go and find the manual and actually find some of the self-organization techniques. Fritzke did a really good job in summarizing it really well. I was impressed, and like I remember him many years after. So I haven't touched this for a long time, very long time, many years. But he did a very good job. The neural gas algorithms, it's Martinez and Schulten, very good algorithms as well. It's good research work. Applications, there are endless applications. Check out also the Kohonen book. It gives you some ideas. He gives some examples of applications he used it for there. Those are some ideas that I have currently, but start with those. The Kohonen book is not on the links, but you'll easily find it. Just Google Kohonen or self-organizing maps. It'll pop up as the book. Any more questions? And please do ask.
I think the net had squares in it, and the later part of the presentation, you ended up with triangles. Did you consider any other shapes like pentagons or hexagons?
So I'll explain. This is the topology you're working with. Like usually when you create a geometrical entity, eventually a mesh, you don't use pentagons. It just, you can always convert it into triangles. You do sometimes use surfaces because they have something called parameterization that are very easy, and this is why you use grids. So this is why those two. However, those things are extendable into 3 dimensions. You can do tetrahedra that learn in 3 dimensions. It's possible. It's like the algorithms, they actually, Fritzke has something called growing cell structures. And this can be implemented in multiple dimensions, can be in 4th and 5th dimension. You cannot visualize it, but you can create those creatures. The question is whether it's useful. It
just seems to me the hole detected at the back of the helmet would have been better found if triangles weren't being used, squares were being used.
Can you speak louder, because I can barely understand what you're asking.
Sorry, it just seems to me that the hole, the blue lines at the back of the helmet might have been more clear to the algorithms if a different structure was being used.
No, those are, I want to go too much into computational geometry, but the purple lines you see here, there's a reason. It's the machine learning algorithm that learns is not as good, is not perfect. Those lines, the fact that they're purple, means that it's the learning algorithm learned the mesh wrong. This is something that I added on top, because the mesh is composed of surfaces and the surfaces should be smooth. The blue lines you saw before are edges of the surface. So those are outliers, and I just marked them so I will be able to see it, and you can correct them later. Actually, I can try to. There's actually algorithms here now if I press the correct button. Let's see, I think this is this one. Yeah, you see, it eliminated all the things that are wrong. And now the blue lines represent the areas, and now you can try to learn again. I think this is like that. Yeah, this is only Hebbian learning. This is, at the points as they are, this is what it will tell as Hebbian learning. You can implement Hebbian learning without moving the points. But when you implement it together with moving the points, then this is what happens. Those are not perfect. Just like many machine learning algorithms, they are flawed. However, think about it. Whatever it did well here, it did very well. It's very hard to get good algorithms to do this level of compression and do it in a level that represents density and gives such nice triangles. So there are trade-offs here. That you think about it. You don't know the topology of whatever the object you're learning. It tries to learn it, and sometimes it does pretty well. Did I answer your question?
Yeah, I think you did. Thank you.
Oh no, thank you. Thank you for asking. If you have more questions, I'll be more than happy to answer.
Okay, thanks.
I guess this is for the organizer, but how often are these meetings held? This is my first time at one of these.
Sure, we meet every month, the second Monday of each month.
Okay, thank you.
And for everyone who's new, our topics are all over the place. Often we'll have kind of advanced topics, a lot of theory and demonstration, kind of such as this. Other times we will get into algorithm basics and everything in between. So
how does one become a speaker? I given like a bunch of talks. So I'm new to Austin, and I gave like a bunch of talks at various meetups in my previous city.
Sure, just reach out to myself or Tyler, and yeah, we would love to have you.
Oh, thank you.
We'll pay you in t-shirts and pizza.
Someone said something about t-shirts? Like, I like
Not for you, Jacob.
Jacob, you already have a t-shirt.
Yeah, I have an algorithms t-shirt actually, but I'm wearing not the algorithms one. I'm wearing the one from PyCon Israel.
Jacob, you should admit it. You want more T-shirts. Just admit it.
No, I collect them. I collect them. I like the t-shirts. Actually, the algorithms one, I do have one.
You can never have too many free T-shirts. Well, Jacob, thank you again for an excellent talk. I really enjoyed it. For someone like myself, who's definitely not an expert in this domain or works in this domain the day-to-day, it was pretty illuminating and definitely piqued my interest. So thank you again.
Thank you for inviting me. And we're going to stop the recording now and hang around.
Yeah, we could stop the recording and hang out for a little bit. I have another commitment a little before 8, but I'm good otherwise.
Okay. Tell us when we're done.